All right. So like I said, the last little bit for Unit 8, we're going to talk about how to do the Nernst equation and how to calculate like the mass of the electrode, that'll increase or decrease depending upon which one it is. So just to review, for number, oh, you guys need textbooks. For number 6, this is just calculating the standard free energy change and the equilibrium constant. So in order to do this, what is free energy? What symbol does that have? Delta G. So we're going to calculate delta G standard, and what else are we calculating? The equilibrium constant, which is K. So in order to calculate both of these, page 845, by the way. In order to calculate both of these, we need the standard cell potential for this reaction. We need to calculate E. All right? So let's split our reaction into the two half reactions. How many, or what are our two half reactions? Pb2 plus makes Pb. Where are the electrons? On the left, and we have how many? 2. And then what's our second half reaction? And the electrons are on the right there. Good. So in the chart on page 845, look up the reduction potentials for both of these. Which one are we going to flip? Which one's not reduction? Yep, the magnesium one is oxidation, so we're going to have to flip the sign for that one. Let's go ahead and look up those two values, because we're going to need that for this problem. 845. It's on 845. Oh, okay. It's like, no, I'm right. You're wrong. So what is the standard reduction potential for the lead equation? What is it? What is it in the chart? Negative 0.13. Are we flipping that one? No, because that's already reduction. We don't want to flip that. So that's going to stay as negative 0.13. It's okay for an individual piece to be negative, as long as the overall cell, E of the cell, is positive. All right? So what is magnesium's reduction potential? What's its reduction potential? Negative 2.37, but since this is oxidation, we need to flip it to positive 2.37 volts. So what is E of the cell? 2.24. And that is volts. Okay. So now that we have E of the cell, we're going to calculate delta G and we're going to calculate K. So the delta G equation from E of the cell looks like this. Negative NFE. Yes, ma'am. Yes, that is on the formula sheet. So the NIFE equation, I don't want to say nifty because then that makes you think temperature's in the formula, so it's NIFE. Hasn't earned the T. So, well, temperature here would be 298 Kelvin because it's standard. So it is given, technically. So to calculate delta G, we're just going to plug in. Now, N is the moles of electrons. So how many electrons do we have? 2. F is the Faraday constant, and that is on your formula sheet. I'm trying to remember if it's the rounded one. It's not 96. It's 96485, or it's 96500. Okay, 96485 is on your formula sheet. 96485, and that is coulombs per mole of electron. And then E is 2.24 volts. A volt is the same as a joule per coulomb. So that's why we can use this, because if you look, moles of electrons are going to cancel, coulombs are going to cancel, and we're going to be left with joules, which is the unit for delta G. So go ahead and calculate delta G. All right, so what do you get as your delta G? All right, so negative 432,000 joules. And let's think about that number. It's a negative, which means, what does that tell us about the reaction? It's proceeding in which direction? In the forward direction. Negative delta G means it's proceeding in the forward direction, means it's favorable in the forward direction. What does our positive E cell tell us about the reaction? It's favorable in the forward direction. That's how they're related, okay? And then to find K, we're going to use what equation? The retweet that link equation. Negative RT ln of K. That's an old hat. We've done that before. So plug it in. Remember, for delta G in the retweet that link equation, you need delta G in joules because the R that you use has joules. That was a common mistake I saw on the Unit 7 test and the Unit 7 group quiz, which I have those graded. We'll go over them at some point. And that was a common mistake I saw, was a unit mismatch. So negative 432,000 joules equals negative 8.314. What's our temperature, Jonathan? 298 Kelvin. And then ln of K. Ooh, I'm struggling to keep that on the board. All right, so then when you solve this, when you get it all, you should get 174 equals natural log of K, or around 174. So what do you get as your K? Actually, before you give me what you got, do we expect K to be greater than or less than 1? Greater than 1. Because we have a negative delta G and we have a positive E. All right? So if you don't get a K greater than 1, you've done some math wrong. Maybe you lost the negative sign in front of the RT ln of K. That was another thing I saw. Even though this formula is on your formula sheet, there's no excuse for getting the formula wrong. I can kind of understand using the wrong R value because that you have to know which one to use, but I cannot understand why you would get a formula wrong, especially one that's given to you. All right, so what do you get as your K? I got 5.31 times 10 to the 75. Did you just do e to the 174? Okay, so I just did e to the answer. And so, did you get times 10 to the 75? Then you'll be fine. As long as you're in the same order of magnitude, you're good. Okay, cool? Questions on that? All right. Can I go to the next page? All right. So this one, 7A and 7B, nope, sorry, 7B is using the Nernst equation. 7A, that is stuff you should already know how to do because we did that, the past couple of classes. We just reviewed that in the last problem. So take a minute or a couple minutes to go through that one, okay? Okay, so to go through this one, just a quick review. What are my half reactions?
Zinc solid goes to zinc 2+.
Where are the electrons?
Right side.
Yep. And what is that E?
Positive 0.76.
Yep, because this one is oxidation, so you have to flip the sign. In the chart, it is negative. And then my other half reaction is, yep, and the 2 electrons are on the left. And E for that is what? Yep, 0.34 volts. So my overall equation, which we're going to need for later, what's the overall cell potential? 1.10 volts. Okay, so that's part A. All right, so for part B, what we're going to do is the concentrations of those ions have changed. Actually, for the zinc ion, we changed it. Here, what are the concentrations of the zinc and the copper ions? 1 molar because it's standard. That means standard. Yes, 1 molar because standard. That is a very grammatically correct sentence right there. So if we change the concentrations, the voltage or the cell potential will change. So that is using the Nernst equation. And I have bad news for you. The Nernst equation is not on the formula sheet. And this is what's, okay, a little frustrated about this. No, I think it's named after somebody's who figured it out. Some guy. Probably a white guy, European, who's probably dead already. Yeah, that's typically what happens with science, yeah. So the Nernst equation used to be on the formula sheet. And then they took it away. But then they still have asked questions where knowing the Nernst equation is beneficial. So when I go through it, I'll explain to you like the types of questions they would ask still. So the Nernst equation is this. E of the cell equals E of the standard cell minus 0.0592 over N times log of Q. Yeah. Wow. Hey, I have it memorized. The guided notes goes through the derivation of this. 0.592 is the combination of F, R, and T. The Faraday constant, the R value, and the temperature at 298. Okay, that uses all of that. That's why it just reduces down to 0.0592. N is still moles of the electrons. Q is the reaction quotient. Okay, that's the actual concentrations of these substances at this point in time. E of the cell that has a little degree sign, that's our standard cell potential, which we just calculated in 7a. E without a degree sign is the cell potential of this actual cell. Okay? So, before we go into how to calculate this, let's talk about how Q will affect the cell potential. Okay? Can Q ever be negative? No. But yeah, because you can't have negative concentrations. Q will be greater than or less than 1, right? Or I guess it also could be 1. When Q is 1, what happens to this whole term? 0. So when Q equals 1, we're doing E standard cell, minus 0. So E of the non-standard cell equals E of the standard cell. So therefore there would be no change in the voltage. So if we change both concentrations to like 0.5 molar, Q is still going to be 1. Okay? When Q is less than 1, oops, that was a weird Q. When Q is less than 1, what happens to this whole term here? Okay, let's back up. What is log of a number that's less than 1? Negative. It's negative. So you're going to end up doing E cell minus a negative, so it'd be E cell plus some term. Some term X. So E cell, E non-standard cell would be greater than the standard cell. Okay? When Q is greater than 1, what happens to this term? Well, log of a number greater than 1 is positive, so you're just going to be subtracting a term. So E, it's going to be E cell minus some term X. So E of the non-standard cell is less than E of the standard cell. So the voltage would decrease. Bye. Okay? Now, once we go through the calculation of this, we'll talk about why this happens and why the voltage increases or decreases conceptually. All right? But like what I wrote in pink is kind of the types of questions that they ask about this. So instead of actually calculating what would be the new voltage, they say, if I were to change the concentrations to these, or if I were to increase this concentration or decrease this concentration, how would that affect the voltage? So you kind of need to know how to find Q. You don't actually need to be able to calculate Q. I mean, you do for some things, but you kind of need to look at how Q will affect it. Okay? Either multiple choice or free response. Okay? So let's actually calculate E of the non-standard cell for this problem. Okay? So E cell equals, what was my standard cell potential? 1.10 volts minus, we have 0.0592. What's my N? 2, because my reaction here, I had 2 electrons being transferred. Okay? So over 2 times log of Q. Well, okay, let's look back at our reaction. What's our Q expression? What's our Q expression? Zinc 2 plus over copper 2 plus. Why did I not include the zinc metal or the copper metal? Because they're solids. So it's the ion of your product over the ion of the reactant. So remember, it's always products over reactants. Okay? So my zinc 2 plus ion concentration here is 1 times 10 to the negative 4. And then my copper ion concentration stayed as 1.0. So before we even do the calculation, is Q greater than or less than 1? It's less than 1, so my E of this non-standard cell, my voltage should increase. Okay? But let's actually calculate what it would be. And then we'll talk conceptually. So what do you get? Have you gotten there yet? All right, what do you get? 1.22? Which goes along with our prediction. But now to explain why. So remember, our reaction was this. I'm just going to rewrite it. Cu2 plus zinc going to zinc 2 plus Cu. Okay? We didn't change the concentration of the copper 2 plus ion, but we did decrease the concentration of this. Our concentration of this decreased. Think about Le Chatelier's principle. When you remove a product, which way does the reaction shift? To the right. Remember, you shift towards removals. So since we removed a product, the reaction is now going to proceed more in the forward direction, meaning that it's more favorable in the forward direction, which means an increased voltage. Okay? This is actually the reason behind Le Chatelier's principle. Back in Unit 4, when we were talking about it, you were just like, oh, you just memorize. Remove, shift towards it. Add, shift away from it. This is actually the reason why. okay? And it has to do with the driving force of the reaction. So I'm going to write it out. Removing zinc 2 plus leads to an increase in driving force of the reaction. Therefore, an increased voltage. Okay? Don't worry, you're going to do another practice problem with that. Are we good there?
Yes.
A couple of people are still writing. When you're done writing, go ahead and flip to number 8. And 8 is going to be like the same type of problem as 7, A and B. It's just all as one instead of split up into two different ones, okay? All right, can I go to the next page? All right, why don't you guys attempt number 8? Actually, hold on. I need to explain how to get the reaction started because there's a slight difference with this one. Okay, so for this one, actually, to get started, what we need to do is figure out which reaction is going through oxidation and which one's going through reduction. So so we have silver and silver plus 1 and cadmium plus 2. Let's actually write out those reduction equations, look up in the chart to figure out which one we're going to have to flip. Okay, because up until this point, you've been given the reaction. Okay, so what is my reduction equation for silver? Ag, well, if it's being reduced, we have to start at the higher oxidation state. So it's going to be Ag plus an electron going to Ag. And then for the other one, we're going to be Cd2 plus how many electrons? 2 going to Cd. So take a moment, find both of those equations in the chart. Be aware that there's a silver 2 plus going down to silver plus in the chart as well. You have to find the correct ones. And I'm going to write down the exact values from the chart, not the flipped one. We'll talk about how to flip it in a moment. So what do you get as the silver reduction potential? 0.80? And what about the cadmium? Negative 0.40. Good. Okay. We talked about this a few classes ago. I know it's been a while. We had that lovely wind day. Whichever value is more positive, that's going to be the one that's going to stay as reduction. So the more positive value, the higher positive value stays as reduction, and the more negative one has to be flipped because that's going to go through oxidation. So which one are we going to flip? The cadmium. We're going to flip this. So really, this is going, I'm just going to cross through it. You can still see it though. So it's going to be Cd going down to Cd2 plus 2 electrons, and the E is positive 0.40. All right. So now, to write your full equation, you're going to need to balance that. So you're going to have to make the electrons equal. But you can calculate, so in order to make the electrons equal, what are we going to multiply this first equation by? 2. What does that do to the cell or to the potential?
Nothing.
Nothing. That was a trick question. This is like the one case where when you multiply the coefficients, it doesn't do anything to the constant. Okay? So go ahead and find E of the cell and then use the concentrations, use the Nernst equation and all that stuff. Practice what we just did with number 7. All right, so going through, what did you get as E of the cell? 1.20. And what's our overall equation? Let's get that written down too. Okay. So, now plugging that into the Nernst equation. What is our N? 2. Now, our Q expression is going to be what? Our expression. CD2 plus? Good. We have to square that silver ion concentration. Don't forget that the coefficients become the exponents in Q and K expressions. All right. So, for CD, I lost my spot on my page, we have 1.5, and that's going to be over 0.2 squared. Now, actually solving this is not typically going to be a question that you're going to see on the AP exam. But just explaining what's going to happen to the voltage definitely will be, can be, okay? That's fair game. So our Q, is our Q less than or greater than 1 or equal to 1? It is greater than 1 in this case. Okay, it is greater than 1. So will our voltage increase or decrease? Our voltage should decrease. It should decrease. Okay, we'll go over the conceptual in just a little bit, but let's actually calculate it. Knowing how to calculate is something I'm asking you to do. So what do you get as the cell potential? .15. We're going to ignore the sig figs of the concentrations. So 1.15 volts. And that matches our prediction. The voltage did go down. Now the reason why is looking at our overall equation. We decreased the concentration of silver and increased the concentration of cadmium. Both of those causes a shift in which direction? To the left. Decreasing a reactant is going to cause it to shift to the left. Increasing a product is going to cause a shift to the left. So both of these end up decreasing the driving force. Okay? Okay, both of them decrease the driving force of the reaction, therefore leading to a smaller voltage. And leading to a more positive delta G. It'll still be negative because our E of the cell is still a positive value, so delta G would still be negative. It would just be less negative than had it been at standard conditions, 1 molar of everything. See how it's all coming together? All right? Did you have a question? Okay. No, I thought I handed it up. All right. Okay, the last two problems are calculating using the amps, the current flow that's going to be, right? Isn't amp measurement of current? Is it current? I don't know physics well enough. But using the amps to figure out, yeah, it's current. Because it's coulombs per second. That makes sense. But using that to figure out like the mass that your electrode is going to change by. Okay. And now just remember, the cathode, what was it? The fat cat gets fat. The red cat gets fat. The cathode, the fat cat gets fat. The cathode is the one that's going through reduction. That is going to increase in mass because it's going from the ion to the metal. The anode is going to lose mass as the reaction proceeds because it's going from the metal to the ion, okay? So in this, in number 9, we're looking at just 1/2 reaction. We have, we're going to calculate the mass of copper metal that is produced during the passage of 2.50 amps of current, oh, it is current, it says it right there, through a solution of copper 2 sulfate for 50 minutes. Okay, so a few things. An amp, I said this already, but an amp is the same thing as a coulomb per second. All right, so what is our reaction that we're doing here? What are we starting with? Copper 2 sulfate. What part of that copper 2 sulfate do we care about? The copper 2, the Cu2+. This is forming what? Cu, copper metal. Is it gaining or losing electrons to do that? Gaining. So the electrons are on the left, and it's gaining 2 of them to go from Cu2+ down to Cu. So basically what this question is asking is what mass of this am I going to form? Did you have a question? No, it just, I had a weird too. All right, this is all stoichiometry. So there's no memorization of a formula, it's just learning the process. In stoichiometry, my big hint is always start with a singular unit. You start with a unit that is not a compound unit. An example of a compound unit is amps, because it's coulombs per second. An example of a singular unit is minutes. So we're going to be converting minutes to grams. I know, it doesn't, we're going to be going from minutes to grams using things like the amps. And, shh, where else have you seen coulomb? The Faraday constant. The Faraday constant. So let's start with 50 minutes. What do you think we need to get minutes to? Seconds. How many minutes in a second? Or how many seconds in a minute? Okay. What can I convert seconds to? Coulombs. I can use the amps to convert seconds to seconds to coulombs. So it's 2.50 coulombs per 1 second. That's an amp. All right. I want to get from coulombs to grams. Okay, the Faraday constant. Remember, the Faraday constant is 96485 coulombs per 1 mole of electrons. Okay, and that's on your formula sheet. You do not need to memorize the Faraday constant. So here, 96485 needs to go on the bottom so that coulombs will cancel. And 1 mole of electrons go on the top. How many moles of electrons were in this equation? 2. So 2 moles of electron are going to go on the bottom. That's a 2, not a weird D. And what's going to go on the top? 1 mole of copper. Then I can go from mole of copper to the grams of copper using MM on the PT. And it's been a while since you've heard that. I'm teaching that to my academic chem kids right now. What is the MM of Cu on the PT? Don't worry, we're done. And that's Cu. So at this point, minutes cancel, seconds cancel, coulombs cancel, moles of electron cancel, moles of copper cancel, and we're left with grams of copper. Oh, I just realized mole of electron looks like mole with a dash. Because, yeah. Whew. 2.47? 2.47 what? So that means that whatever mass of copper we had originally, we're going to gain 2.47 grams of it. So the mass will increase by that if we run that current for 50 minutes. Okay? That's what that means. I know, going from time to mass. You didn't think it could be done, but it can. All right, the last problem is calculating. Are we good? We good here? All right, the last problem is same type of concept, but we're going to figure out the oxidation state of the chromium. So we have an aqueous solution of an unknown salt of chromium. Chromium likes to form what type of charge? Positive. Just some sort of positive charge. We're figuring out what the number is. Okay? So we're going from some, I'm just going to put it as x plus, some positive charge. We're going to figure out what x is. And we're converting it to chromium metal. We're told that we produce 1.94 grams of chromium metal. Because if we run the current for 3 amps for an hour, okay? How many electrons does the chromium X plus need to gain in order to form chromium? X electrons. Okay? We're solving for X. We're solving, find X. There it is. Anyway. All right. What information can we calculate from the givens? What's something we can calculate? Moles of what? All right, let's calculate moles of chromium metal. That's easy, right? 1.94 grams of chromium. Convert that to moles. What's the molar mass of chromium?
Yeah,
52.00 because it's like 51.9996 or something like that. It might just be 996. I might have added an extra 9. 996. I'm still pretty impressed that I remembered that. I know. I'm just so awesome.
0.0373.
0.0373? All right, that'll be information we'll use later because we can't go any further with that. We can't then convert that to moles of electrons because we don't know how many moles of electrons we have. How can we find the moles of electrons that we have? Convert hours to moles, right? Using the time and the amps. So, what am I starting with? Okay, or 1 hour, which is the same as 60 minutes, which is the same as
3,600.
that is 1 hour. Just an FYI. If you need to do the individual steps, I'm not going to judge you out loud. It's okay. So, what am I converting seconds to? Coulombs. Because an amp is a coulomb per second. What am I converting coulombs to? Moles of electrons using 96485 coulombs and 1 mole of electron on the top. I don't know why I'm saying it like that. Seconds cancel, coulombs cancel. We're left with moles of electrons. How many moles of electrons is that? Yes, I got 0.112. Yep. Okay. So in this reaction, we have X of moles of electrons for every how many moles of chromium? 1. So we can set up a little ratio. What does that equal? Come on, pen. 0.0373. Same ratio, right? So now how do you solve for X? Cross multiply and divide, right? Couldn't you just divide because you have 1 here? Work smarter, not harder, right? So what do you get as X? X is 3. So, did we answer the question? No. Because we had to state what the oxidation state was. So the oxidation state of the chromium ion was Cr 3 plus or plus 3. Boom. Mic drop. I'm not going to drop my pen because it's brand new. What? Drop mic. Peace out. I don't know.